This conference will now be recorded.
Hello everyone. So we are starting a new chapter which is redox reactions. So first of all we have to know this importance of redox reaction, but before that what this term actually means, that is what is the meaning of redox, that we have to do. So first the topic is importance of redox reaction, then we will see classical concepts of redox reactions, then redox reactions in terms of electron transfer, which is the modern concept, then oxidation number, rules for calculation of oxidation number, valency versus oxidation number, and redox reactions in terms of oxidation number and fractional oxidation number, and there will be problems also. So what is the meaning of this term redox, which is basically combination of two terms, one is reduction, another one is oxidation. So what is redox reaction? The word redox, it is comprised of these two terms together. So together we are calling is RED, red, and the OX, these two letters from the word oxidation. Together we are getting a new word which is redox. So when we are saying that it is a redox reaction, basically both these processes, that is reduction process, oxidation process, both will occur simultaneously. So as for example, here you can see two equations are written and there are some numbers written above the atom. Though right now you will not be able to fully understand what these numbers mean, because these numbers are basically oxidation number. But just to give you an example of what is redox reaction, I have here these, I'm showing these two equations. Okay. So these numbers are basically oxidation number that we will discuss in detail. But here as a preliminary idea, if we say magnesium metal is reacting with oxygen, and here oxidation number of magnesium is 0, for oxygen also it is 0, and once the reaction is complete, now the oxidation number is changed for magnesium. So from 0 now it is +2, and for oxygen also it is changed from 0 initially, now it is -2. So there is just change in oxidation state. So in this case, from 0 to +2, that is number is increasing. This is basically loss of electron and it means it is oxidation. Similarly, the other process, that is from 0 to -2, it is basically going towards negative. That means it has gained some electron. So gain of electron is basically reduction. So here you can see both the processes are occurring simultaneously. And in the second equation also we have MnO2, we have hydrochloric acid, and in the product side we have MnCl2, manganese chloride, we have chlorine gas, and we have water also. Now here oxidation number for all the atoms, left hand side, right hand side, both are written. So for Mn it is +4 after reaction +2, that means it has gained 2 electron. Then -2, here also it is -2, there is no change in oxidation number for oxygen. For hydrogen also it is same, +1 before, after also +1. For chlorine also there is no change. Sorry, in this case there is no change, but -1 if you consider chlorine gas, it is 0. So there is change basically for manganese and only for chlorine, not for H or oxygen. So here when we talk about reduction oxidation, basically there is change in oxidation number, that is we will discuss in detail. So here just primary idea you can get from these two equations, what is redox reaction. But what is the importance of this redox reaction? Why we have different separate unit for this redox reaction? That means these reactions there must be some applications. So redox reactions, they are basically basis of electrochemistry. Electrochemistry, that is another unit which is in class 12. So in electrochemistry, if we do not have prior knowledge of reduction oxidation, obviously we will not be able to understand electrochemistry. It is all about redox reaction, that is reduction and oxidation. So this unit is completely based on redox reactions. Now they have different types of laboratory application as well as industrial application. Laboratory application means it is small scale application. Okay, we can qualitatively or quantitatively we can find out some cation that is present in a particular salt. So for that we have to know we should have clear idea about redox reaction. Otherwise, the theory of those experimental that is observations will not be able to understand. And industrial application means if there is some large scale preparation method manufacturing of any particular compound, then also redox reaction has some applications. The charging and discharging of electric battery, that is also redox reaction that we see in day-to-day life. And this statement that you are seeing, that is a third statement, that is also basically related to this electrochemistry chapter. So in electrochemistry chapter, there is a topic based on battery. So some battery we can once it is, that is the power is charge is finished, we can again that is it is already discharged, we can again charge it. That means charging, discharging, both are possible. So that is a two types of batteries are there, but whatever is the type of battery, we have to know the redox reaction if we want to understand the theory of how the battery works. Respiration process on which our life depends. This is another example of redox reaction. So in this case, what happens? Glucose molecules that is present, basically the food that we are taking, that is basically oxidized, and the oxygen molecule that we are taking from air, that are basically reduced, and ultimately after reduction it is converted to water. So this process on which that is we are living on respiration. So this is also example of redox. Industrial level, redox reactions are used for extracting metals from their ores. So in ores, metals are present basically in different oxidation state. Suppose I am talking about iron, it is present in +3 oxidation state in its ore. Now from +3 state, if we reduce it by some application of suitable reducing agent, then from Fe3+ state, after gain of 3 electron, now it will be converted to Fe0 state. So right now, if you have little bit of confusion regarding these numbers, it will be gradually clear when we actually discuss what is oxidation now. So from 3+ after gain of electron, now it is converted to actual metallic state, which is 0. There is no oxidation, there is no excess electron or no deficiency of electron. It is 0 oxidation number. So if we want to, that is, extract metal from its ore, that is, it will be in some oxidation state, and after reduction, or it will be in metallic state. So we want them, after extraction, we basically want them to be in metallic form, and because natural existence in ore, that is not the metallic form, that is in some positive oxidation state, because ultimately they are metals. So that is why we do extraction so that we can get them in metallic form. And so when they're present in ores, they are in oxidized form, and after extraction they will be in metallic form, and we need some reducing agent. So these are some applications of redox reactions, and that is why they are so important, and that is why we are having this separate unit that is based on this type of reactions only. Classical concept of redox reaction. Now the modern concept of redox reaction, that is wholly based on number of electron transfer. Just the previous example, remember Fe3+, it is gaining 3 electron and it is converted to Fe0. So this is basically modern concept. We always talk about electron. We never talk about whether there is addition of any particular element or not. It is completely based on electron transfer. But classical concept is different. Oxidation reaction, if we consider classical concept, then there are different types of we can give the definition for oxidation in different ways. So we will see them one by one. So oxidation reaction may involve any of the following. So the first equation that you are seeing here, carbon plus oxygen, we are getting carbon dioxide. So it is basically addition of oxygen. Now addition of oxygen to what? To carbon, obviously. Now when there is addition of oxygen to any particular element, then you can say that that element is basically oxidized. So this is an oxidation reaction example. Now if there is addition of any electronegative element, suppose it is not oxygen, but here we have the electronegative element sulfur. So sulfur is attached to iron. Iron, it is in that is metallic form. Now sulfur is attached and we are getting ferrous sulfide. That means now this is also example of oxidation reaction, because in this reaction there is addition of some electronegative element, sulfur. Okay. Now the third way you can define oxidation reaction is removal of hydrogen. So here we have H2S plus bromine. Now from H2S you can see after the reaction is over, there is only sulfur left. That means from H2S now hydrogen part is gone and sulfur now it is in its elemental form, sulfur only. So you can say that this is also third way you can define oxidation reaction, which is removal of hydrogen. Now the fourth type, removal of electropositive elements. So not just hydrogen. In place of hydrogen, if there is removal of some electropositive element. So here we have which electropositive element? Just focus on potassium iodide. Here we have the electropositive element K potassium. Now after the reaction there is only iodine. That means from Ki, K part is gone, only iodine is left. So that is why with respect to iodine there is removal of electropositive element, which is potassium in this case, and this is also example of oxidation reaction. So when we are talking about addition, it is basically oxygen or any other electronegative element, and when we are talking about removal of any atom, it is basically hydrogen or any electropositive elements. So these are the ways we can define oxidation reaction. It may involve any of these four processes. Now we can define oxidizing agent. It is that substance which oxidizes other substances. Now just consider these four reactions. In these four reactions, what are the species that are actually oxidizing the other substance? So in the first equation, it is basically oxygen, which is oxidizing agent. Then in the second example, sulfur is the oxidizing agent. In the third example, bromine is the oxidizing agent. And because bromine is helping in the removal of hydrogen by accepting hydrogen itself, so it is oxidizing agent. And in the last example, hydrogen peroxide is the electropositive element, because ultimately this HO part that is actually taking this potassium part. So these are the four oxidizing agents for these particular four particular examples. Now we will see what are the different ways by which reduction reactions we can define. So reduction reactions also may involve any of the following processes. Here we have seen addition of oxygen, but now just look at the right hand side. It is basically addition of hydrogen, as if reverse of this. So with nitrogen, hydrogen is added, we are getting ammonia. This is example under this category. Then addition of any electropositive element. So here we have addition of electronegative element. Now we are saying addition of any electropositive element. Here we have tin chloride and HgCl2. After reaction, there is essential for Hg2Cl. That means if we look at HgCl2, this is the positive part, electropositive element. It is metal atom. This is halogen. Now it is HgCl2, but if you look at the right hand side, one mercury is extra added. Now the formula is Hg2Cl2. So this is with respect to HgCl2, this is addition of electropositive element. So if we just focus on these two parts, it is addition of electropositive element. Which element? Mercury. Then the third one, removal of oxygen. So here you have to focus on zinc oxide. From zinc oxide, this oxygen part is gone. And you can also compare with this third example, which is removal of hydrogen in the left hand side when we talked about oxidation reaction, but now it is removal of oxygen, as in reverse of removal of hydrogen. So zinc oxide, now it is only zinc, there is oxygen removed. So that is why it is removal of oxygen with respect to zinc. And the last example, removal of electronegative element. In this case, we have seen removal of electropositive element, that is an oxidation reaction, left hand side. And here it is removal of electronegative element. Which electronegative element? FeCl3. After reaction it is FeCl2, that means one chlorine part is removed. So that is why it is electronegative element removal. Now just we have defined oxidizing agent in the previous case. Here also you can define reducing agent in these 4 examples. So reducing agent is a substance which reduces other substances. So in the first example, hydrogen is the reducing agent. In the second example, SnCl2 is the reducing agent. Okay. Then C, carbon, that is the reducing agent in the third example. And in the fourth example, here again hydrogen is the reducing agent. Okay. So it is reducing agent in both first example and the fourth example. So in this way, we can define reducing agent. Now, if you carefully look at all these 8 examples, one thing you will see, as we have said, that reduction oxidation, they happen simultaneously. Now, in the left hand side, we have only talked about oxidation. And in the right hand side, we have only talked about reduction. Then how it is happening simultaneously? Basically, it is happening simultaneously because just consider this example, H2S Br2. So if you focus on H2S, it is removal of hydrogen and it is sulfur is now only present, there is no hydrogen. So with respect to H2S and S, it is obviously oxidation of sulfur. But if you look at bromine species and HBr, this is basically addition of hydrogen to bromine. Now addition of hydrogen is basically reduction. That means if you focus on these 2 species, it is basically reduction. Now it may be a little confusing for you because under oxidation there are so many different types of ways we are defining it. Reduction also there are 4th ways we are defining it. But this is classical concept. Remember, when we talk about the modern concept, which is electron transfer, then you will see it is more general, and then you don't have to remember all these separate different ways. That is addition of oxygen, addition of electronegative element. These separate definitions we don't need. There will be a common definition which will cover all the types of reactions together. So that is, it is the modern concept. Fine. This is classical concept. Now in classical concept, some more discussion still left. We will do that, finish that. After that, we will see the modern concept. So a substance which undergo oxidation, obviously that will act as reducing agent. So here, if you see, which is itself undergoing oxidation. Now itself undergoing oxidation means H2S. Here sulfur is undergoing oxidation. That means H2S is helping bromine to reduce. So here H2S will be the reducing agent. So a substance which itself is undergoing oxidation, now it will be behaving as reducing agent. And similarly, a substance which undergoes reduction, it will act as oxidizing agent. So here we have chosen this example which you have already seen. With respect to AgCl2 and Ag2Cl2, it is basically reduction, R. But if you look at this, electronegative element chlorine, here only 2 chlorine per SN, here 4 chlorine. That means addition of electronegative element. That means it is oxidation. Now if it is so, then SnCl2 is basically undergoing oxidation. Which undergoes oxidation itself acts as reducing agent. That means this compound is the reducing agent. Okay. And the substance which undergoes reduction, that means AgCl2 is undergoing reduction. So it will be acting as oxidizing agent, OA. In any chemical reaction, in one of the reaction is oxidized, obviously the other one is surely reduced. So oxidation and reduction, they always takes place simultaneously. Fine. Here the word redox was coined for this class of chemical reactions. Which class of chemical reactions? There are basically different types of chemical reactions, different categories actually. Redox is one of the term where there will be reduction reaction as well as there will be oxidation reaction. Fine. Now In this example, there are total 4 species. Before reaction, 2 species, after reaction, 2 species. But suppose if you are thinking that what about this type of simple reaction? Here it is true that carbon is undergoing, it is addition of oxygen, so it is undergoing oxidation. Electronegative element oxygen is added. But how the reduction is occurring? If you are thinking that, then that is basically oxygen, it is converted to now CO2. Now with respect to oxygen, it is basically reduction. But if you simply follow the classical concept directly, you will not find any, you cannot choose any of these ways, because with oxygen there is addition of carbon. Now it is not addition of oxygen, it is not addition of hydrogen, it is not also any addition of electropositive element, because carbon is not very electropositive, it is not very electronegative also, it is something in between. Then how you will define with respect to oxygen, how you will say that it is undergoing reduction? Now under this situation, the modern concept, which is electron transfer, that concept will help you. And this electron transfer, that is also based on oxidation number. So here C plus O2, it is easily you can say that carbon added, that is oxygen is added to carbon. So according to the definition of that addition of oxygen, it is oxidation reaction definition. So carbon is undergoing oxidation. But how we will say that oxygen is undergoing reduction? Because that you cannot find any of these options. So then we will take the help of the other concept, which is electron transfer. So here we have this in this slide. The most widely applicable definition of reduction oxidation is basically this one. So when we say oxidation, you don't have to think about whether it is addition of an electronegative element or removal of an electropositive element. Just think about whether there is loss of electron or not. It is simple, right? Compared to the previous, all these definitions. And reduction, obviously, it is the opposite process, that is gain of electron. So here we have this simple diagram, there is no compound mentioned. Simply suppose some species are present, which is there is electron retained on this circle. So it is basically electron donor, and there is another circle which is another color. After reaction, this pink one, it is accepting electron from the blue one, and now the electron is over this pink circle, and the blue one, there is no electron retained. So if you focus on the blue part, it is basically losing electron. So it is undergoing oxidation reduction. But remember, it is sacrificing electron, it is donating electron towards the pink one. And pink one is accepting electron. And it is accepting electron, that is why it is undergoing reduction. But as it is accepting electron, it is itself the oxidizing agent. So this is the oxidizing agent. This is the reducing agent, the blue one. Okay. If you consider the reverse reaction, suppose you are moving from this side to this side, then it will be opposite. Now the pink one is sacrificing as if electron. So this is the general definition and easier also. So redox reaction involves transfer of electron. So in terms of separately, if you say oxidation is loss of electron, reduction is gain of electron. Now when you are using the word redox, that means both are occurring. So now it is better to say that this type of reaction, there is some transfer of electron from one species to another species, between two species. Now we know that electrons, we cannot create it, we cannot destroy it. That means it will always occur in pair. That means if in any reaction there is loss of electron, that electron, it is not that we can destroy that electron. So that electron must be taken by some other species. So that is why these two processes have to be simultaneously. Otherwise, how we will explain this fact that electrons neither created nor destroyed? As it is neither created nor destroyed, so that is why both these processes, that is oxidation reduction, both these processes should occur simultaneously. Otherwise, we cannot, that is, it means that as if electrons are created or destroyed, but that is not true. So there are two parts, remember, in any redox reaction. One is reduction half reaction, another one is oxidation half reaction. Now, why we are saying half reaction? Because here the total reaction that you are saying, you can break this reaction in two parts. Suppose I am writing this blue one only. Okay, suppose this is the pink one. Here electron is present, and now I will change the color. So this is from pink to pink. This is basically reduction. But if I am drawing only the blue part, then it is sacrificing electrons. So this is basically oxidation. So this is equation number 1. This is equation number 2. When you add these two equations, then you get a complete full reaction. But you can always break them in two parts. One is oxidation, another one is reduction. But remember, when you are writing these half reactions, this electron you have to write it separately, as if it is like this. Here we have written it over it, but as if it is like this, because this electron, it is still free. Someone will take it, and that taker is present here. So that is why when we will write the half reactions, we will write the species plus electron like this. Okay. So the species, so when I'm saying species, it may be any of these. It may be some ion, not necessarily it has to be something neutral compound. It may be ion carrying some charge, positive, negative. It may be atom, simply atom, or it may be molecule, compound. So the species that accepts electron, whatever it is, ion, atom, molecule, whatever it is, if it is accepting electron, then it means it is oxidizing agent. So now we have this broader definition of oxidizing agent. Previous definition we are now not considering. So by accepting electron, obviously it oxidizes other species. And the species that donates electron, that will be called reducing agent, and it is sacrificing its own electrons, and that is why it is reducing the other species. So this is the definition of oxidizing agent and reducing agent when we are considering redox reactions in terms of electron transfer. So electron is transferred from one species to another species. Now we have to know oxidation number. So we will use this number several times. So that is why you have to, this is very important, we have to understand it very carefully. Oxidation number, it is defined as the imaginary charge. So don't think that when I am putting some charge over some compound, just take the first example in today's class, the first slide, there is written +2 and -2. So I'm writing this, but that doesn't mean that there is actually charge present. It is the imaginary charge. And why we have imagined it? Because that will help us to understand oxidation reduction reaction. So that is why we are imagining this. Imaginary charge appears on the atom in a molecule, or not necessarily molecule, it may be any ion also carrying some charge. Suppose I am writing any anion, CrO4, 2-. Overall charge is 2-. So here also we can put oxidation number. Now, how this imaginary charge is appearing? When electrons are assigned in accordance with some arbitrary rules. We will use some, see some rules, and we will apply those rules. These are very simple rules and nothing very complex. So on the basis of those rules, with some arbitrary rules, on the basis that electron pair in a covalent bond belongs entirely to more electronegative unit. Now what it means? Suppose you have bond between two atoms A and B. Now A and B, they are obviously different element. Now suppose B is more electronegative than A. That means here the electrons that are present, as if you can think as if these electrons are entirely belong to electronegative. It is actually not true. That is, in reality, that doesn't happen. That both the electrons, suppose B is more electronegative, so these two electrons, it will be exactly over B. That actually doesn't happen. But we will think it as if A is that is, it will have some positive charge and B will have some negative charge. Why? Because B is more electronegative. So this idea we have to put when we will calculate oxidation number, that any covalent bond, the electron pair as if entirely to more electronegative element. So that is why here we can see this Mg we have written +2, and over oxygen we have written -2, because we know that oxygen is more electronegative. Okay. A term that is often used interchangeably with oxidation number, there is another term that also more or less used for the same purpose, and that is known as oxidation state. So in the whole unit, that is, we can use any of these two terms, no problem, and both are actually means as if same thing. Okay. When the atom loses electrons, its oxidation state increases. That means it will be going towards more positive. And when the atom gains electron, in oxidation state decreases, so it will be going towards more negative. Suppose initially it is +2, after accepting it is 0. That means from +2 to 0, it is decrease in oxidation state. That means it is gaining electron. Similarly, if the atom is losing electron, suppose if you consider the reverse direction from 0 to +2, that means it has lost 2 electrons, -2 electron. So this process, oxidation state is increasing. That means it is losing electron. Losing electron is oxidation. Okay. So from this direction, if you consider it will be loss of electron. But if you consider this direction, it is basically +2 electron. So this is basically reduction. This is basically oxidation. The term oxidation number represent the positive and negative character of the atom. So as I have written here, +2 over Mg2, Mg, and over oxygen I have written -2. So it means that Mg, suppose if you do not know whether oxygen is more electronegative, then just looking at this, now you will be having the idea that yes, as there is negative charge, that is the less number is given over oxygen, that means oxygen is negative character. That is, in between these two, if we compare, oxygen is towards negative, that is electronegative element compared to Mg. Similarly, Mg is carrying the oxidation number which is higher, +2 is higher than -2, so that is why it will be having the positive character. So when in a particular, in this compound there is only two elements, Mg and O. Suppose there are 3 elements or 4 elements, normally 3, 4, that is rare. So if we write all the oxidation number, you will be getting the idea that which one is positive, which one is negative. Electrons shared by two like atoms divided equally between the two atoms. So two like atoms, that is same atom. Suppose there is A bond, or I am writing here chlorine, chlorine. That means it is diatomic chlorine molecule. So if it is so, then electrons are shared equally. So in this case, you cannot write +1 or -1 because both are same. We cannot say that it is more electronegative like that. So in this case, what will happen? We will consider zero oxidation state for both the chlorine. It is same for oxygen also, then for hydrogen. Fine. So electrons shared between two like atoms, that is same atoms, divided equally between the two atoms. But when it is not same, that is unlike atoms, then the electrons will be assigned to more electronegative element. So suppose if there is I'm saying suppose NaH, this compound. Now sodium is more electropositive. H is also electropositive, but if you compare, sodium is more electropositive. So that is why positive charge will be over sodium, negative charge will be over hydrogen. Now if you are thinking then that in MgO I have written +2 and -2, but why I am writing here +1 and -1. Now that depends on that is, once we cover all the rules, this confusion will be clear. Fine. So we will now see the rules one by one. the oxidation number, in short ON, of an element when it is free atomic state. Free atomic state means simply atoms. That is how we represent elements, by their symbol. Or if it is in polyatomic state. So these are the atomic state. But suppose if you are considering their natural state. Natural state means hydrogen, it remains a diatomic gas. Then carbon, natural form is graphite. Chlorine, it remains as naturally chlorine diatomic gas. P4, phosphorus, it is basically tetraatomic P4. So then also it will be considered as 0 because you have just all the same atoms. You do not have two different atoms. So obviously it will always have oxidation number 0. This is the first rule. Now the second rule is monoatomic ion. Oxidation state is equal to net charge. So suppose we have ion sodium plus. So when we are talking about Na plus, obviously its oxidation number is +1. You don't have to calculate it because there is nothing to calculate. And oxidation number for chlorine, chloride basically. So in chloride ion, the oxidation number of chlorine is -1. So the name of the ion is chloride, but actual element we use the term chlorine. So the statement will be the oxidation number of chlorine in chloride ion is -1. Similarly, you can say monoatomic ion, calcium. Now calcium will have oxidation state +2 because sodium it is from group 1, and in group 1 oxidation number cannot be more than +1, and here it is 2 plus because for group 1 general if we see the general electronic configuration, it is basically after noble gas it is NS1. That means once it is losing one electron, it is basically reaching the noble gas configuration, which is very stable. So there is no tendency for group 1 elements, I'm talking about S block, group 1 elements, there is no tendency to lose the second electron because that will break the noble gas configuration. So that is why maximum oxidation state, and they, not just maximum, it is the only oxidation state possible for its block group 1 is +1. So that is why it is always +1. And for calcium 2 plus, it is the second group, that is S block group 2. Here the general electronic configuration for all the group 2 elements is noble gas. After that it is NS2. That means after losing 2 electron, now it will reach the noble gas configuration. So that is why their common oxidation state and the only oxidation state possible is 2 plus. So that is why calcium, which is from group 2, it will have oxidation state 2 plus. Next, the algebraic sum of oxidation states of all atoms in a molecule is equal to 0, whether it is ion or that is, sorry, it is only for neutral molecule, but suppose if it is ion carrying some charge, then the algebraic sum of oxidation state of all the atoms, it will be equal to the charge of the ion. So we will take two examples. Suppose a neutral molecule is H2SO4, and in the same molecule there is sulfate ion. So I will write it here SO4 2 negative. So this is basically ion and this is basically a molecule. So for molecule, the algebraic sum of oxidation state. So here total 3 elements we have: hydrogen, sulfur, oxygen. Now for hydrogen, the oxidation state, it is always +1. It cannot have any other. Now for sulfur, here we will have 6 +6. Now if you are thinking how I am calculating that idea also you will get. Right now just focus on this rule, what it is actually saying. Later it will be clear how we are getting this +6. So sulfur is +6 and oxygen is basically -2. Now how to take this algebraic sum? +1 for hydrogen, but how many hydrogens are there? Total 2, so it will be 2. Then how many sulfurs are there? Only 1, that means 6 will come only once. How many oxygens are there? There are total 4. So 4 into -2, it is basically -8. Now if you take the sum, it will always be 0. Basically what we do when we have 3 elements, as this rule is saying that overall it will be always 0 because the molecule is after all neutral. You cannot have any residual charge. What we do, hydrogen and oxygen, it is mostly +1 and -2. For hydrogen, it is always +1. In some rare cases, it is -1, which is hydride, that you will see separately. And for oxygen also, it is mostly -2. So whenever you are getting any compound like this, then what we will do, for hydrogen and oxygen, we will put these values 2 and -8. And suppose you do not know the oxidation number for sulfur, because oxidation number for sulfur, it may vary. It is not that it is always +6, it may be +4, it may be -2. So as variation is high, chance of variation is high for sulfur, so what you will do, you can consider it as if it is X. And you already know that overall it is 0. That means in this case, from this equation, you can get the oxidation state of sulfur, which is +6. So basically, we take the help of this rule that overall it is 0. So we take the advantage of this tool, and it helps us to calculate the oxidation number. Similarly, if it is SO4 2-, now while calculating, suppose you do not know sulfur, I am writing here X, but you know for oxygen it is -2. So X plus -2 into 4, which is -8. Now overall charge, now do not write 0 because now overall charge is -2. So X is equal to 8 - 2. Again, we are getting the same result for sulfur. So this is the third rule. Now the fourth rule, hydrogen has oxidation number +1 in all its compounds except metal hydride. Now remember what we have said, that more electropositive element, it will always be having the higher oxidation state comparatively. Now hydrogen, we know it is already electropositive, but more electropositive elements, even compared to hydrogen, that type of elements also present, and mostly they are S block elements. Now S block metals basically. So it is sodium, potassium, lithium, calcium, magnesium. So when you will have these S block elements, group 1, group 2, and you will have hydrogen with them, now obviously all these elements are more electropositive compared to hydrogen. Now hydrogen cannot have +1. So it will always be having -1 value. So for example, if I am writing NaH, Na is +1, this is -1. But remember, for calcium, these are called hydride. Metal hydride, that is the general term. When I am writing NaH, it will be sodium hydride. When I am writing lithium H, it will be lithium hydride. Then potassium hydride KH. But remember, for group 2 elements, Mg, Ca, now the formula is CaH2. Because calcium will lose 2 electrons. And these 2 electrons will be taken by 2 separate hydrogen. That means per calcium there will be 2 hydrogen atom accepting electron. So that is why it is Ca2 plus, and it is -1, but 2 times it is there. That means overall negative charge will be -2. So 2 plus 2 minus, it is ultimately 0. Similarly for Mg also, it will be having the formula H2. So 2 positive charge is coming from calcium, and -1 it is coming from hydrogen. Overall it is 0. Okay, so this is the fourth point, that is for hydrogen atom special. The fifth rule, now this is based on now we are focusing on oxygen. The oxidation state of oxygen in most compounds -2, as I have said. Remember, during the calculation of oxidation number for sulfur, we have already by default considered for oxygen the oxidation number is -2. Exceptions you will find only in some cases. Which are the cases? If you have any peroxide compound, then its oxidation number is -1. If you have any superoxide compound, then its oxidation number is -half. Okay. If you have any compound of oxygen with fluorine, then oxidation number will be positive. Why? Because if you compare electronegativity of these two elements, fluorine is more electronegative. Now, if you have any OF compound, which compound? There are basically these two compounds well known. One is O2F2, another one is OF2. So in these two compounds, as oxygen is comparatively more electropositive, I should not say more electropositive, I mean to say F is more electronegative. So oxygen is less electronegative. So positive charge will be over oxygen. Now OF2, for fluorine, you can have maximum that is oxidation state possible. It is always -1. So it is -1 for 2 fluorine. That means overall total negative charge is -2. So for oxygen, it will be having charge +2. Similarly, when it is O2F2, then also -2 is the overall negative charge. So overall positive charge is +2, but it will be distributed over 2 oxygen. So this is the case when you have, this is the third case, when you will have compound between oxygen and fluorine. What about peroxide and superoxide? So in peroxide, what happens? Oxidation state is -1. Example of peroxide is, very common example is H2O2. So H2O2, if you write the structure, it is HOOH. Now if we know hydrogen is more electropositive, so it will be always plus. So if you remove these two, remaining charge is like this: oxygen -1, -1. So individually, if you see, it is each oxygen there is -1, -1 charge. So that is why it will be having this type of charge. Then what about superoxide? So in superoxide, I will give example. Common example is KO2. Now we know for potassium only one oxidation state is possible, which is +1. Always only one is possible. That means as a whole the molecule is neutral, so the total negative charge, it must be -1, but there are total 2 oxygen atoms. So this -1 charge, it will be distributed over 2 oxygen atoms. So ultimately it will be -12 and -12. So when oxygen is having -12 charge, then we call those oxides as superoxide. And when it is having -1 charge, it is peroxide. Another example also we can give, which is Na2O2, example of peroxide. And if we have normal oxide, then it is -2. So except these two cases, but these are not, you will not find many. Mostly it is -2. And also remember, when we have compounds with fluorine, then also it will have positive oxidation state. Next rule. Next rule is specially for halogens. This is for oxygen. Now what about halogens? So halogens, they are basically from group 17. They have one common oxidation state, which is -1. Now we know fluorine is the most electronegative element in the whole periodic table, and it will always have negative oxidation state. It cannot have positive oxidation state. So oxidation state is -1 in all its compounds because of this reason. Now what about the other halogens? Other halogens means first is F, then Cl, then Br, then I. Now it is always -1, it is more still fine. But others, they are not so electronegative. Now what will happen? It is true that -1 oxidation state, that is also common for them because it is the group oxidation state, common. So when they are appearing as halide ions, halide. So from fluorine, the term we are getting for F- is fluoride. It is ending with IDE. So common term is halide. So for fluorine, you are getting the term fluoride. From chlorine, you are getting the term chloride. From bromine, bromide. From iodine, iodide. So when you have all these halide ions, it will always have -1 charge in their compounds. But suppose when halogens are combined with oxygen. Now, halogen, only we are focusing on these three, that is not F. F is separate. Cl, Bri. Now Cl, Bri, all these three, if you compare electronegativity with respect to oxygen, obviously oxygen is more electronegative compared to Cl, Bri. So if you have any compound between oxygen and chlorine, oxygen bromine, or oxygen iodine, it will, that is the positive side will be towards ClBrI because oxygen is more electronegative. So when halogens are combined with oxygen, for example, oxo acid and oxoanones. Now what is oxo acid? Oxo acid is basically, if I write the general formula, it is something like this. Suppose we have any element capital E. With this element there will be OH, and sometimes with oxo acid there is some double bond O also. It may be more than one, like this. So this is the general structure of oxo acid, and when I am saying oxo anion, just remove this H. Now it will be represented like this. So this is oxo anion. Now one example, if we see for chlorine, one oxo acid I will show here, which is HClO4. Now this is the formula, but if we actually write the structure, it will be, so see here we have one OH and three E double bond O. Just compare with this. Not necessarily it has to be 2 only, it may be 2, 3, or it may be 0 also. So there may not be any E double bond O. So another oxo acid of chlorine I am writing here, which is like this. So here you do not have any Cl double bond O. This you do not have here. So this is also another example of oxo acid, but here we have taken, this is HOCl, here we have taken HClO4. So in HClO4, this is the structure. But if you simply remove this hydrogen, the structure for the oxo anion, it will be like this. So this is basically ClO4 negative ion. Now when you have this type of oxo acid, now obviously halogens when combined with oxygen, they will have positive oxidation number because halogens are less electronegative. Now here oxidation number, it is very easy to calculate. How many chlorine oxygen bonds are there? They are at total 1, 2, 3, 4, 5, 6, 7. So here positive oxidation state, that will be +7. Similarly here also hydrogen is removed, but you still have 7 chlorine oxygen bonds, so it will be +7. Now it is not that you always have to draw structure, though it is better if you can draw the structure, just to verify that from the formula the calculation that you are doing whether it is correct or not. So suppose from formula, if we are calculating oxidation number, how we will do so? For chlorine, suppose it is X, we do not know. Overall the molecule is neutral. For hydrogen you have to assign +1. For chlorine there is only one chlorine, it is X. And for oxygen, for each oxygen -2, so it will be -8. So +1 + X -8, overall it is 0, so X will be equal to 7. That we have already seen. Similarly for ClO4, it is X negative -8, overall charge is -1. So X will be equal to 8 - 1. Again we are getting the same value, which is +7. So here we have these two examples. Oxo acid example is HClO4 and oxo anion example is ClO4-. Now the next rule, that is for alkali metals. Alkali metals for group 1, like this, sodium, potassium, potassium, and for alkaline earth metals, group 2. So for group 1 it is always +1, and for group 2 it is always +2 in all their compounds. So this is very easy to remember, and when we will actually that is another unit is there which is based on S block. When you will read that unit, you will be able to remember it easily. It is not very difficult. Now one example I can give, suppose we have any sodium compound NaCl, then I have also give you a little different example, Na2O2, not so very common, but still here also it is +1, here also +1. So you will not get any compound where you will not get plus. It is always +1. For calcium, suppose we have CaSO4 calcium sulfate, it is +2. We have calcium oxide, it is +2. We have calcium chloride, it is +2. So it is always +2. For coordination compounds, this is a special type of compounds. There is separate unit for that, where we have this special type of coordination bonds. It is more convenient to use oxidation number of the ligands. We know when we have coordination compounds, very easy example, if we see NiCN whole 4, overall the molecule is neutral. Sometimes it may not be neutral also. Suppose I am writing K3FeCN6. Now if you remove this 3 potassium ion carrying total 3 positive charge, if you remove this part, now the remaining charge will be here 3 negative. So it may be some anionic coordination compound or it may be neutral also. Now in this case, we use oxidation number of ligands as a whole. So here it is true that we have total 3 elements, nickel, carbon, nitrogen. But separate oxidation state we do not consider for carbon and nitrogen. We together consider for this ligand, which is the ligand Cn minus. So together overall charge is Cn minus. So don't calculate separately the charge of C and N. The structure is like this. 4 Cn coordination bonds will be there. So here we will consider for each Cn as if it is a single atom. So it will contribute -1 charge. Okay. Sorry, there will be overall charge. I forgot to mention. Overall charge is -2. So it will contribute -1 charge each. That means total negative charge you are getting for negative. Nickel is having +2. That means outside charge is -2. Similarly, here also total 6 cyano. That means total negative charge is -6. Outside charge is -3. That means this is +3. So remember, for coordination compound, it is slightly different. Here for ligands, though this you will, that is separately, this type of compounds we deal with separately in coordination chemistry only, which is in class 12. But for preliminary idea, just remember, for whatever atoms you will have in ligand, separately you don't have to calculate the oxidation state. Both the atoms together represented as anion, or it may be that is neutral ligand also. For example, neutral ligand, any metal, 4 water molecules are attached. So in this case, the overall contribution for each water molecule, suppose total 6 water molecules are there, each will contribute 0. Okay. So separately, hydrogen, oxygen, what is oxidation state, that we don't consider. So we will end the session here. Next day we'll use some examples and we'll try to find out oxidation number based on these rules. So here we have these total 8 rules. Please practice these rules so that next day we can applying these rules, we can actually calculate oxidation number for elements, for atoms in different types of compounds. We'll end the session here. Thank you for listening.